Alright, so in this video I'm going to be explaining an important article, a very interesting article about domain adaptation. The name of their model is called LAMDA. And the title of this paper is LAMDA Label Matching Deep Domain Adaptation. So this is the article in 2021. And by the way, these two are two of the best professors in Monash University in AI, ML, and NLP. Very creative people, very smart people. Both of them are Vietnamese, by the way. So what is the motivation of this interesting paper? Deep domain adaptation approaches have recently been shown to perform better than the shallow rivals with better modeling capacity on complex domains such as image, structural data, sequential data. The underlying idea is to learn domain invariant representations on a latent space that can bridge the gap between source and target domains. Several theoretical studies have established insightful understanding and the benefit of learning domain invariant features. However, they are usually limited to the case where there is no label shift, hence hindering its applicability. In this paper, we propose and study a new challenging setting that allows us to use Wasserstein distance to not only quantify the data shift, but also the label shift directly. Like previous video, I talked about label shift, conditional shift. So these are very important because we have three different domain shifts: concept shift, label shift, and covariate shift. The first one is concept shift. So we develop a theory to demonstrate that minimizing the Wasserstein distance of the data shifts leads to closing the gap between the source and target data distributions on the latent space. For example, your latent space could be an intermediate layer of a deep net. So while still being able to quantify the label shift with respect to this latent space. Interestingly, our theory can consequently explain certain drawbacks of learning domain invariant features in the latent space. So these are the theoretical setting that we consider multi-class classification problem with this label set. So consider the hypothesis family on the source domain, and T is just a mapping. The corresponding hypothesis family is this. The intuition here is that with X drawing from probability of the target, we apply the mapping T to reduce the difference between two domains and then use a hypothesis H sub S to predict the label of X. This motivates us to seek the key properties of transformation in order to employ hypothesis. So we have a transformation going from source to target. To formulate this, this can be a push forward distribution. They drew inspiration from functional analysis. We have similar concept, push forward mapping and push forward distributions and those things, but which consequently introduce a new domain termed the transport domain, having the density function and probability distribution P sharp. So we define the supervisor distribution for the transport domain. To ease presentation, we denote the general expected loss. So we shorten this RAA as RA, and we measure the variance of general losses when predicting on the source domain and general losses when predicting on the target domain. So there is a gap between target and source domains. And now we have just two assumptions, assumption 1 and 2. Assumption 1, first we say that supremum of your loss is finite. The second assumption, we force a K-Lipschitz function on your loss function with respect to a norm over your simplex. And so this is, in mathematics, we call this K-Lipschitz, the constant of the Lipschitz function. So in this theorem, it says that it returning 1 if x is not x prime and 0 otherwise. So for any hypothesis, this equality holds. So there is an upper bound on delta R, because R is just because delta R is just the variance. So there is an upper bound on the variance of between source and target hypothesis. So we consider. So to arrive at a stronger result, we consider Wasserstein distance between Ps and P sharp. And in the theory of optimal transport, which is a very important thing in functional analysis, in probability theory, we are using these ideas for domain adaptation. There is another upper bound on your variance, but let's go to something more concrete. The optimal objective value, this optimal objective value is equal to objective optimization of 3, and we can interpret G sub 1 and T sub 1 as two generators that map the source and target domains to the, so this is G1 and T1. They map the source and target. Source comes here, target comes here, to the common latent space. So we have a common latent space Z. So now we have a latent representation. So our latent representation is here in the middle, because we have source and target. But it goes to the source, and we have a reconstruction error. So whatever you have created, we can have a reconstruction error. So if we employ the JS divergence or F divergence, DOP in 5, this optimization can be further be written as a min-max 4. It is also worth mentioning that with regard to the latent space and the above equipment, we have the following formulation for the source classifier and target classifier. So we have source classifier and we have a target classifier. So we have label shift we measure it with Wasserstein metric. And you see here the label match and mismatch on the latent space. For example, here is the latent space. When source goes to using G and target using T1 map, and source goes using G1 map, and the latent space, we have some label match and some label mismatch. But the label mismatch term has this lower bound. So to strengthen this observation, we develop a theorem to directly offer an upper bound for the L1 distance between the label marginal distributions. To this end, we define a new metric, C tilde. So this is the new metric with respect to family of classifier A. So H sub A is just the family of classifiers. And Z1 and Z2, as I said, is just on the latent space. Then for any Z1 and Z2 on the latent space, if their A is equal, if their classifier says, okay, they are the same, then it leads to their latent is also the same. It turns out that the necessary also sufficient condition is realistic and not hard to be satisfied. We now can define a Wasserstein distance that involves this theorem. So this quantity has an upper bound. So as pointed out by the theory and application study, reducing label mismatch in the joint space when breaching the distance between G1 map and the T1 map on the source and the target domains is a key factor to improve predictive performance of deep unsupervised domain adaptation. A binary discriminator is only able to distinguish the entire source domain from the target domain because you usually use a binary discriminator. You see it in the literature, everybody uses it, but it is saying that here is a very important paragraph. It is saying that hence cannot elegantly guide target samples moving to the most suitable class in the source domain. Our idea is to increase the resolution of discriminators by utilizing a multi-class discriminator D that can simultaneously distinguish source and target domains and emphasize the class regions in the source domain. So with the assistance of a multi-class discriminator, we hope to guide target samples to a suitable class in the source domain. For example, here is in the target we have class, for example, 2. In the target domain, again, we have class number 2. In the source, we have class number 3. In the target domain, this region belongs to class number 3. So it's class-wise, that's why it's more accurate. So the training method, we solve the following optimization for D. Because the discriminator can discriminate the source and target samples and distinguish classes of the source domain. So to train our generator for source and the target, we update them like this. That we move G1 for X drawing from a source distribution to the region of high values by minimizing this I. And then we move T1 for X to, so this reminds us the optimal transport ideas, moving the distribution. We move T1 to one of the class regions in the source domain accordingly, recalling that d sub I represents the likelihood of X with respect to the I source class region. We employ this relation as the cost incurred if we move T1 to DI. So to specify the probabilities that transports X to the source class regions, we use a transportation probability network S, for which S sub I points out probability to transport X, this X, to your D sub I. So this is the total transport cost. So we also push T1 to the region of the lower values of D sub C1 plus 1, which is a region of source samples. So we minimize this the loss on the source domain as well. And we also have a reconstruction term for a better explanation. And then the min-max optimization of our lambda has this form. So K is just the first term for the outer matrix, like 9. For the outer maximum, and alpha TC as in 10 for the inner mean. So the pseudocode is this. First, we are given some source and target. Then we should provide the generator and the classer. We should model that. In order to do that, we go for training iteration. We sample mini-batch because we need both source and target. Then we update using this equation 9. This is very important. We update using that. Then we update G1, this transformation that I said, using the solution of this optimization problem. And we always use this TSNE algorithm because it's a visualization algorithm. Now, when we go from this source to this target, then you can see the results. Because LAMDA is the model of this paper, and ResNet is not using this idea. So you see different classifications when we go from one source domain to the target domain. But the LAMDA, which is the model of this paper, you see the classification accuracy is pretty high. Because in ResNet it was only 41, but now 41% is added to that. So it's a great improvement. Also, you can see the classification accuracy on digits and natural image. So you see even for another data set, you can see that different models, these are different models, but LAMDA has a higher accuracy, especially from this MNIST source. When you go to MNIST M, you have a very high. Also, when you go from Street View to the MNIST data, you see 99% accuracy. But it's high because it's just a classification accuracy.